Okay, so today I shall discuss the total concept of hybridization. Okay, so at first we have to know what is hybridization. Hybridization means intermixing of orbitals, because we are here discussing hybridization of orbitals. So hybridization means intermixing of orbitals of similar energy or nearly similar energy, okay, to form a new set of orbitals of equivalent energies and shape. Okay, so hybridization means intermixing of orbitals of same energy or nearly same energy to form a new set of orbitals having new set of orbitals of equivalent energies and shape. Okay. So this is the definition of hybridization of orbitals. Okay. Now this is totally a theoretical concept. Okay, hybridization idea. Hybridization means, that is the, you can see the name of the topic, that is hybridization, that come from hybrid. Okay, hybrid means that is not pure. Okay, so hybridization means that is some mixing is there. So in that case, what is the mixing? That is intermixing of orbitals of same energy or nearly same energies to form a new set of orbitals of equivalent energy and shape. Okay, now this is totally a theoretical concept first proposed by scientist Pauling. Scientist Pauling first proposed this concept, L. Pauling, in the year 1931. Okay, so this is totally a theoretical concept which is first proposed by L. Pauling in the year 1931. Okay, so he pointed out that in a simple molecule, for example, in methane molecule, CH4, we know that CH4 is methane. Here the carbon atom forms 4 bonds. Okay, the carbon atom forms 4 bonds with hydrogen. Okay, carbon atom forms 4 bonds with hydrogen. Now, in carbon, we know the electronic configuration 1s2, 2s2, 2p2. Okay, this is carbon. So here valence orbital, valence shell is, that is s orbital and p orbital. Okay, in s orbital 2 electrons are there, that is 2s2, and in p orbital 2p 2 electrons are there. Okay, so if it form bonds, then as 2 different orbitals are there, s and p, so different bonds can be formed, but actually 4 bonds of methane is equivalent, all having same bond length, same bond order, same bond strength. So it only possible if mixing of S and P will occur. From this idea, he proposed hybridization of orbitals. Okay, so in the year 1931, first this idea came from chemist L. Pauling to describe, to explain the equivalency of 4 bonds of methane. Okay. Okay, so this is the theory, this is the historical background of hybridization of orbitals. Okay, so next we shall discuss the characteristics of hybridization. What are the characteristics of okay, so first characteristics of hybridization, number 1, the most important characteristics is the number of hybrid orbital forms equal to the number of orbital that are intermixed or hybridized. Okay, so the first point is the number of hybrid orbitals are formed is equal to the number of orbitals gets intermixed. Okay, so this is the most important characteristics, that is the number of hybrid orbitals are formed is equal to the number of orbitals get intermixed. Okay, So let's explain this one. Suppose one S is mixed with one p orbital. Okay, so we get two number of sp orbitals. Okay, if one S is mixed with two number of p orbitals, we will get 2 plus 1, that is 3 number of sp2 orbitals. Okay, in this way if we mix one S with 3 p orbitals, it gives 1 plus 3, that is 4 number of sp3 orbitals. Okay, so maximum number of p orbital is 3, that is px, py, pz. Okay, next 1 s, 3 p and 1 d orbital. Okay, so d orbital for which element? That is transition elements. Okay, so for transition elements d orbital is involved. So here 1 is 3p and 1d, that is 1 plus 3, 4 plus 1, that is 5 number of sp3 d orbitals are formed. Okay, next 1 is 3p and 2 number of d orbitals intermix to give 1 plus 3 plus 2, that is 6 numbers of sp3 d2 orbitals. sp3 d2 orbitals. Okay, next one is 3p and 3d combined to give 7 number of sp3 d3 orbitals. Okay, understand? So the number of orbital intermix to give total number of hybrid orbitals. Okay, next second point, second characteristics, number 2, the hybrid orbitals after hybridization that are formed are always their equivalent in energy and shape. So the hybrid orbitals, are equivalent, the hybrid orbitals are equivalent in energy and shape. Okay, the hybrid orbitals are equivalent in energy and shape. Okay, so if one S and P combine to give two sp orbitals, so the sp orbitals what are formed after hybridization always equivalent in energy, that is 2 sp orbital will be same energy, will have same energy, and the shape also same. Okay, shape also same. So no difference of the hybrid orbital that formed after intermixing. Okay, clear? Third point, point number 3, that is the hybrid orbitals that are formed, they have directional properties, that is they are directed in space, so thus the molecule have some definite geometry. Okay, so that hybrid orbital, the hybrid orbitals are directed in space and define the geometry of the molecule. Okay, so these three characteristics of hybridization is very important. The first one is most important. Okay, so please note that. Okay. Next we'll discuss the conditions of hybridization, in which case hybridization will occur and which case hybridization will not be occur. So next we discuss characteristics of hybridization. Characteristics already discussed, then conditions. Okay. So the first condition is only the orbitals which are present in valence shell participate in hybridization. Okay, so only the orbitals present in valence shell participate in hybridization. So only the orbitals present in valence shell participate in hybridization. Okay, suppose in carbon 1s orbital is there, 2s and 2p. So in between three orbitals, valence orbital means the greatest quantum number, that is 2. So 2 has 2 orbital, that is s orbital and p orbital. So 2s and 2p only can participate in hybridization. Okay, 1s orbital will not participate in hybridization. Okay, so only the orbitals present in valence shell will participate in hybridization. Only the orbitals present in valence shell will participate in hybridization. Clear? Okay. Next. Number 2. The orbitals which participate in hybridization must have small difference in energy. Okay, if the difference of energy of the participating orbital is very high, then hybridization will not occur. Okay, so the difference of energy between the participating orbital, the participating orbitals must not be very high. Okay, must not be very high, otherwise hybridization will not be occurred. It should be very low. Okay, preferable very low. Small difference will be good for hybridization of the orbitals. Okay, so these two conditions is very important condition for hybridization. Clear? Okay. So next we discuss different type of hybridization. So in this section we shall discuss different type of hybridization. So at first we will discuss sp hybridization, where intermixing of s1s and 1p orbitals. Next, sp2 hybridization, where 1s and 2p orbital will mix to give 3 sp2 hybrid orbital. Next, sp3 hybridization, where 1s will mix with 3p orbital to give 1 plus 3, that is 4 sp3 hybrid orbital. Next, sp3d, where 1s 3p orbital and 1d orbital will intermix to give 5 sp3d hybrid orbital. Next, sp3d2, where 1s 3p and 2d orbital will intermix to give 6 hybrid orbital. And finally sp3d3, where 1s 3p and 3d orbital to give 7 numbers of sp3d hybrid orbitals. Okay, clear? Note it down. At first, type of orbitals. Okay, so at first we discuss sp hybrid orbital formed by 1s plus 1 p orbital. Okay. So for example, in beryllium fluoride, okay, BeF2 molecule, in BeF2 molecule. So before finding the hybridization, we have to first find the central atom. We have to find the central atom. So here BeF2, two element is there, beryllium and fluorine, in which the electronegativity of fluorine is higher than beryllium. Okay, so electronegativity of beryllium is less than fluorine. Okay, so we should take beryllium as central atom because its electronegativity is lower. Okay, so more electropositive element will be considered as central atom. So here beryllium is central atom, and its hybridization, we have to find its hybridization. So beryllium is central atom or central element. Clear? Okay. But in case of the molecule where hydrogen is attached, suppose NH3, we should take the element other than hydrogen as central atom. Okay, so in this case nitrogen is central atom. Clear? Okay, so we have to find the hybridization of beryllium in BeF2. In BeF2. Okay, so beryllium fluoride BeF2. Which one is the central atom? Beryllium. Its electronic configuration, what is the Z value for beryllium? Hydrogen, helium, lithium, beryllium, 4. Okay, so its electronic configuration 1s2 2s2. We know that one orbital can accommodate maximum 2 electrons. Okay, so we can write it as beryllium, one box represent one orbital. So this is 1s and this is 2s. Okay, so 2 electrons in each orbitals. Okay, and the p orbital of beryllium is vacant, 2p is vacant. Okay, so 1s2 2s2. Clear? Okay, so here valence cell is 2s and 2p. 2s is filled up and 2p is vacant. Okay, so now hybridization will occur. 1s will mix up with 1p. Okay, 1s will mix up with 1p to give 2sp orbital. So here 3p means 2p orbital means px, py and pz. Okay, so in that case 2s orbital will mix up with 2pz orbital because they are in a same plane. Okay, 2pz orbital. So 2s will be mixed up with 2pz to give 2sp orbital. So after mixing, what happened? After mixing, what happened? Beryllium 1s no change, 1s no change, and 2s and 2pz mix up to give 2sp orbital of same energy. Okay, 2sp orbital of same energy, and 2p orbital will unaffected. Okay, so number of electron in 2s is equal to 2, right? So according to Hund's rule, we have to fill up it first this way. Clear? Okay, so each sp orbital contained one electron. Okay, now it will be, this electron will form covalent bond with fluorine. Okay, so 2 fluorine gives 1 electron, fluorine and fluorine, to form 2 covalent bond. Okay, now how the sp orbital are directed in space? How the sp orbitals are directed in space? The sp orbitals formed are directed in space in this way: beryllium, and this is one sp orbital, and this is another sp orbital. Okay, so what is the bond angle here? Bond angle is 180 degree. Okay, now it will combine with p orbital of fluorine in this way, so formed a covalent bond. Here one electron and here another electron to form a covalent bond, and here also it will combine with another fluorine, okay, to form a covalent bond. So the molecule is look like, it's a linear molecule: beryllium, fluorine, and the bond angle will be 180 degree. Clear? Okay, so this is sp hybridization. In sp hybridization, the molecule is linear in shape. The molecule is linear in shape. Okay, so in sp hybrid orbital, what is the percentage of s character? Percentage of s character, that is equal to 50%. And what is the percentage of p character? That is also 50%. Clear? So in sp hybridal, percentage of s character is 50% and percentage of p character is also 50%. Next we come to the another type of hybridization, that is sp2 hybridization. sp2 hybridization. In which type of molecule it is found? Boron trifluoride. Okay, so in this case again also ethylene, that is double bonded carbon, is sp2 hybridized. Okay, sp2 hybridized, double bonded carbons are sp2 hybridized. Okay, so here boron atom is the central atom. Here boron atom is the central atom. So in boron we know that it is electronic configuration 1s2, 2s2, 2p1, right? 1s2, 2s2, 2p1. Okay. Now intermixing will occur with 1s with 2p because it's a sp2 hybridization. So 1s and 2p will mix up to give boron 1s unaffected, interacted, and 2s and 2p orbital, 1 2s orbital and 2p orbital will mix up to give 3 sp2 hybrid orbital and 1 p orbital, 2p orbital will be unaffected. Okay. So how many numbers of valence electron here? Here number of valence electron is equal to 1, 2, 3. So 3, 1, 2, 3. Okay. Now these 3 electrons will combined with fluorine atom, okay, to form 3 covalent bond, 3 BF bond. Okay. Now how these sp2 hybrid orbitals are directed in space? How these sp3 hybrid orbitals are directed in space? Okay, they are directed in space like trigonal planar. So B this way, and this way. That is trigonal planar. sp2, 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 trigonal planar. Okay, and next this the fluorine atom will combine. Fluorine atom will combine okay. So to form 3 covalent bond, and what is the bond angle? The bond angle is 120 degree. The bond angle will be 120 degree. Okay, and the shape of the molecule is trigonal planar. Trigonal planar molecule. Okay, trigonal planar molecule. Clear? Okay. Okay. So in that case, the percentage of S character in sp2, percentage of S character will be 33.33, right? And percentage of P character will be 66.66, right? Okay. Okay. We'll discuss it later. Okay. So next, sp3 hybridization, where one S will combined with intermix with 3p orbital to form 4 sp3 hybrid orbital. The simplest molecule is CH4, that is methane. So in carbon, the electronic configuration is 1s2, 2s, 2 2p 2. Okay, 1s2 2s2 2p 2. So next intermixing will occur 2s and 2p 2. Next intermixing will occur 1s with 3p orbital. So 1s will be combined with 3 2p orbital. So 2s, this is the valence orbital, will mix up with 2p orbital, px, py, pz, 3 p orbital to give sp3 hybrid orbital. So after mixing, 1s will be unchanged, and here 4 sp3 hybrid orbital will be formed. 1 2 3 4. These are all sp3 having same energy, same shape. Clear? So how many numbers of electron before hybridization? 1 2 3 4. So 1 2 3 4. Okay, so it will be combined with 4 1s electron of hydrogen, 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 hydrogen and hydrogen. Okay, to form 4 covalent bonds. Okay, 4 CH bonds, 4 CH bonds. Now how these sp3 orbitals are directed in space? Okay, so this is carbon, this one, this one, this one, this one. Okay, so this is tetrahedral structure, tetrahedral structure. Clear? So this one, see this, 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 this. Okay, now it will be combined with 1s of hydrogen, 1s of hydrogen, 1s of hydrogen, hydrogen, 1s of hydrogen and 1s of hydrogen. So the bond angle, ideal bond angle is for tetrahedral structure is 109 degree 28 minute, 109 degree 28 minute. Okay, so this is the bond angle for ideal tetrahedral molecule. Clear? Okay, next we discuss another molecule. Yes, we will all discuss the S character and P character after discussing the ammonia molecule. Okay, so in ammonia molecule you can see the central atom is nitrogen. So here nitrogen electronic configuration 1s 2 2s 2 2p 3. Clear? 1s2 2s2 and 2p3. Next mixing will occur. This 2s mixed with 3 2p. Okay, so after mixing 1s as usual, no effect, and here 4 orbitals will form 1 2 3 4. 4 sp3 hybrid orbitals are formed. How many electrons are there before hybridization? 1 2 3 4 5. So 1 2 3 4, following Hund's rule. At first the electrons are occupied singly, then pairing will take place. So total 5 electron, 1 2 3 4 5. So single occupy, at first the electrons will be occupied singly 1 2 3 4, then excess electron will be paired. Clear? Okay, now covalent bond only be formed with unpaired electron, right? So here our number of unpaired electron is 3. So here hydrogen, 1s of hydrogen will combine with this sp3, this electron of located in sp3 hybrid orbital. This one also form covalent bond with 1s electron, and this is also formed. Okay, so here 3 sp3 hybrid orbitals, 3 electrons present in sp3 hybrid orbital, 3 unpaired electron will combine with hydrogen to form covalent bonds, NH covalent bonds. Okay, so how it is directed? The sp3, that is in tetrahedral manner, and in tetrahedral structure 3 are covalent bonds and 1, this is the paired electron which present in valence shell but did not participate in bonding. This is called lone pair of electron. This is lone pair. Okay, so the electron pair which does not participate in bonding is called lone pair. So lone pair of electron also resides in sp3 hybrid orbital. Clear? So we can draw the structure, that is nitrogen, this is sp3 hybrid orbital, this is one sp3, this is another sp3, this is another sp3. Okay, so 4 sp3 orbital. So in first sp3 orbital, one lone pair of electron is there. Clear? In other 3, that is one unpaired, one unpaired, one unpaired. So this unpaired will be paired by 1s of hydrogen, 1s of hydrogen, and 1s of hydrogen. Clear? Okay, and a lone pair is reside on the nitrogen atom. Okay, so we can write the structure. That is nitrogen, hydrogen, 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 and a lone pair of electron. Okay, one lone pair of electron. Now you can see in that case the bond angle will not be equal to 109 degree 28 minute. Okay, because here one bond is missing, one actual bond is missing. Okay, so and one lone pair is residing on nitrogen. Okay, so we know that lone pairs have more repulsion power, okay, than the bond pair, because lone pair are free, they can easily repulse the bond pair. Okay, so here this lone pair will push this bond pair, and this lone pair will push this bond pair. So the bond angle between hydrogen nitrogen H bond angle will be reduced from 109 degree to 107 degree. Clear? Okay, so here the bond angle will be reduced due to presence of one lone pair on nitrogen atom. Clear? Okay. Next, another molecule will discussed here, that is water molecule. Water molecule. So H2O, here central atom is oxygen. Its electronic configuration is 1s 2 2s 2 2p 4 2p 4 4 electrons are present in p orbitals. 2p4 means 1 2 3 and then 1 pairing. Okay, so this is the electronic configuration of oxygen. Now here sp3 hybridization will occur. So one s will mix with p orbitals. Okay, so oxygen as usual 1s will be unaffected and 4 hybrid orbital sp3 hybrid orbital will be formed. 4 sp3 hybrid orbital. Okay, how many electrons before hybridization? 2 2 4 5 6. So at first singly occupied the orbitals. Okay, then pairing will takes place. Clear? So here you can see that two lone pair, this one lone pair, this one lone pair, and two unpaired electrons are there in the sp3 hybrid orbitals. So two unpaired electron will be paired with hydrogen, 1s or 1s electron of hydrogen, 1s electron of hydrogen. Okay, so again this is oxygen, this one, this one, this one and this one. Okay, so here this is lone pair, this is lone pair, this is one unpaired and this is one unpaired. So unpaired will be paired by hydrogen, unpaired will be paired by hydrogen. Clear? Okay, so what is the shape of this molecule? It's like oxygen, hydrogen, hydrogen, and here two lone pair, this one and this one. Clear? Okay, so this is V shape. V shape. Okay, ammonia is pyramidal. Ammonia is pyramidal structure. Okay, and this is V shape. Ammonia is like pyramidal. Okay, pyramid. You can see the you know what is the structure of shape of pyramid. Okay, and water is V shaped. This is V shaped. V shaped. Okay, this is V shaped. And what is the bond angle? Again here two lone pair, so bond angle will be more repulsion. Bond angle will be reduced to, here bond angle will be reduced to 104.5 degree. Okay, around 104.5 degree. Okay, so bond angle reduced to 104.5 degree. Clear? Okay, so in that case what is the percentage of s character for sp3 hybrid orbital? S is 25% and P is 75%. Clear? Okay. Next we shall discuss sp3d hybridization. sp3d. Okay, so those molecule, those element having d orbital will may participate in this hybridization. Okay, may participate in the hybridization. For example, PCl5, here the central atom is phosphorus. Okay, so phosphorus has 3d orbital, may be vacant but 3d orbital present. Okay, so phosphorus is a third group element. Its electronic configuration is 1s2 2s2 2 2 2p6 2p6 3s2 3p3 3p3 and 3d has 5 orbitals. One, two, three, 4, 5. 3d has no electrons. Okay, so we only considered the valence cell. So valence cell, we only consider the valence cell. So this is the valence cell, 3s, 3p and 3d. Clear? 3s, 3p and 3d are the valence cell. Okay, so here intermixing will occur, 1s, 3p and 1d. So 1 is 3p and 1d. Okay, to give 1, 2, 3, 4, 5 hybrid orbital, 1, 2, 3, 4, 5 sp3 d orbital. Okay, other d orbital, that is 4d orbital, will not participate. Okay, so how many electrons before hybridization? 2 plus 3, that is 5. So 5 electron, 1, 2, 3, 4 and 5. Okay, so this will combined with chlorine atom, chlorine, 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 chlorine. Okay, to form 5 phosphorus chlorine covalent bond. Clear? Okay, so how these sp3d orbitals are directed in space? Okay, so it's like phosphorus 1 orbitals here, this, this one and this one. Okay, right? So this is TBP structure, trigonal bipyramidal structure, trigonal bipyramidal structure, and this will attached with this chlorine by covalent bond. Clear? Okay, so this is trigonal bipyramidal structure. Or TBP structure, trigonal bipyramidal structure or TBP structure. Okay. Okay, so in that case, what is the percentage of S character? sp3d. Okay, so total 5, so S will be 20%. Okay, P will be 60% and D will be 20%. Clear? So this is TBP structure. Next we move on to sp3d2 structure. sp3d2 hybridization. Okay, for example, sulfur hexafluoride SF6 molecule. Here the central atom is sulfur. So sulfur is valence orbital is 3s 2 3p4 1 2 3s2 3p4 and 3d is vacant 1 2 3 4 5 3d is vacant. Okay, now intermixing with 1s 3p and 2d orbital to give 6 1 2 3 4 5 6 1 2 3 4 5 6. Which orbital? sp3 d2 orbital is formed and 3d are not participate 1 2 3. Okay, so here how many electrons are there before hybridization? 1 2 3 4 5 6. So 5 unpaired electrons will present in sp3d2 orbitals, which will be paired up by fluorine atom, okay. So what is the geometry? The geometry is octahedral. The geometry is octahedral. Okay, so here the geometry will be octahedral. One sulfur atom, this is fluorine, 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 one fluorine up, one fluorine down. Okay, one fluorine up and one fluorine down. Okay, so this is the structure geometry of sp3d2 hybridized molecule, that is octahedral. Okay, now what is the percentage of S character? Three plus 2 5 plus 6, that is 100 divided by 6, that is 16.66. Okay, what is P, percentage of P? That is 16.66 into 3, that is 50, around 50. And what is D? That is 16.66 into 2, that is around 33. Clear? Okay. Okay, finally we will discuss the hybridization of sp3d3, sp3d3. So in sp3d3, the molecule which has sp3d3 hybridization is IF7. Okay, so in IF7 iodine, what is the electronic configuration of iodine? Fluorine, chlorine, bromine, iodine. Okay, fluorine is 2s2 2p5, This is valence electron 2s2p5. This is 3s2 3p5. This is 4s2 4p5, and iodine 5s2 5p5. Clear? So electronic configuration, valence shell electronic configuration of iodine is 5s2 5p5. Okay, 5s2 5p5. Okay, so we'll consider 5s orbital and 5p. Okay, so 5s2 5p 3 1 5p 5 1 2 3 4 5. Okay, now here 5d orbitals present, 1 2 3 4 5, which is vacant. Now here intermixing with 1s 3p and 3d. Okay, so after intermixing 7 orbitals will be formed, sp3 d3 orbitals, 1 2 3 4 5 6 7, 1 2 3 4 5 6 7. So how many electrons before hybridization? 2 plus 2 plus 2 plus 1, 7. 1 2 3 4 5 6 7. It will be paired with fluorine, 1 2 3 4 5 6 7. Clear? Okay, so how sp3d hybrid orbitals are directed in space? That is pentagonal bipyramidal structure. Pentagonal bipyramidal structure. How it look like? Pentagonal bipyramidal structure. As you should draw a pentagon first. This is pentagon. In the center of the pentagon, the central atom. Okay, so here 1 2 3 4 5. So here fluorine 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 fluorine, and one fluorine is up and one fluorine is down. So this is pentagonal bipyramidal structure. Okay, pentagonal bipyramidal structure. Okay, so in this way you can in the previous way you can calculate the percentage of S character, P character and also D character. Okay, so what is the percentage of S character here? .28. Okay, what is the percentage of P character? 42.86, and also percentage of D character is 42.86. Clear? Okay, so we discuss so far SP hybridization, sp2 hybridization, sp3 hybridization, sp3d hybridization, sp3d2 hybridization, and sp3d3 hybridization. Okay. Now sp3d2 hybridization has two types. One is sp3d2 and another is d2sp3. Okay. It will be discussed later in coordination chemistry chapter, that is inner orbital or outer orbital complexes, okay, based on the strong field and weak field ligands. Okay. Now finally, before conclusion, we shall discuss some tricks to find the hybridization of molecule. Okay. The tricks is, at first, suppose a molecule is given here, beryllium fluoride, BF3, CH4, ammonia, water, PCl5, SF6 and IF7. So we want to know the hybridization of the central atom. Okay. So at first we have to find the central atom, that in that case beryllium, here boron, here carbon, here nitrogen, here oxygen, here phosphorus, here sulfur, here iodine. Okay. So next we have to find the valence electron of central atom. Okay. The valence electron of central atom. Next we have to add the number of monovalent atom. Okay, number of monovalent atom. Now we have to divide it by 2. Clear? We have to divide it by 2. If the result is 2, then we'll say it is sp hybridization. If the result is 3, we can say this is sp2 hybridized molecule. If it is 4, we can say it is sp3 hybrid molecule. If it is 5, we can say this is sp3 dehybridization. If it is 6, we can say it is sp3 d2 hybridization. If it is 7, then it must be sp3 d3. Okay. So let's check each and every molecule. So this is our formula. That is number of valence electron of the central atom plus number of monovalent atom divided by 2. This is for neutral molecule, right? This is for neutral molecule. If the molecule have positive charge or negative charge, for positive charge we have to subtract the number of positive charge from the upper value, and for negatively charged molecule we have to add sufficient number of electron to the upper side. Okay, we'll discuss it. So for beryllium fluoride, BeF2, so what is the number of valence electron? That is 2. So here for beryllium fluoride, that is 2 is the valence electron. What is the monovalent atom attached to it, the beryllium? 2. So 2 plus 2 equal to 4 by 2, that is equal to 2. Clear? So 2 means sp. Okay. Next, BF3. Next BF3, that is boron, that is valence electron 3 plus 3 monovalent fluorine attached 3 divided by 2, that is equal to 3. 3 means sp2. Clear? For CH4 carbon 2s2 2p2, that is 4 valence electron plus 4 hydrogen attached divided by 2, that is equal to 4, that is sp3. Okay, clear? Ammonia valence electron, how many valence electron? 2s2 2p3, that is 5 valence electron. So for ammonia, 5 valence electron plus 3 hydrogen attached divided by 2 equal to 4, that is sp3. Clear? For water, 2s2 2p4, that is 6 valence electron plus 2 hydrogen attached divided by 2 equal to 4, that is sp3 again. Clear? Okay, next come to PCl5, phosphorus group 15. So number of valence electron equal to 5. Okay, like nitrogen plus 5 chlorine attached monovalent divided by 2 equal to 5. 5 means sp3d. Clear? Next sp6, sp6 group 16. So 6 valence electron like oxygen plus 6 fluorine divided by 2. Sorry, this is oxygen sulfur 6, yes, 6 6 12 by 2, that is 6, that is sp3d2. Clear? Iodine halogen group 17 means 7 valence electron plus 7 fluorine divided by 2 equal to 7, that is sp3d3. Clear? Okay, now finally we discuss some charge species. Charge species, suppose SO4 2 minus. So what is the hybridization of SO4 2 minus? So here the central atom is sulfur, right? Okay, so sulfur, what is the valence electron in sulfur? Group 16, so 6 is the valence electron plus how many number of monovalent atom is attached? How many number of monovalent atom is attached? Monovalent 0, because oxygen's valency is 2, it is not monovalent. Yes, so that is 2 plus, as the molecule is negatively charged, so we have to add this. Okay, so this is 2 divided by 2, that is equal to 6 plus 2 by 2, that is equal to 4. 4 means we can say this is sp3 hybrid molecule. Clear? Okay, next molecule NH4 plus ammonium molecule. Okay, ammonium ion. Okay, ammonium ion. So nitrogen group 15 means 5 valence electron. How many monovalent atom attached? 4. Okay, now as it is a positive charge, so we have to minus 1. Okay, because 1 positive charge means 1 minus 1. 1 negative charge means 1 plus 1. Clear? Okay, divided by 2. So 5 plus 4, 9 minus 1, that is 8 by 2, that is 4. Which hybridization? sp3. Clear? Okay, next. Yes, negative charge, the number of negative charge will be added, and for positive charge the number of positive charge will be subtracted. Okay, next, carbon dioxide CO2 hybridization. Here the central atom is carbon. Hybridization, group 14, carbon in group 14, so 4 is the valence electron, plus no monovalent atom is attached. Oxygen is bivalent, so 0. Neutral molecule, so that is equal to divided by 2, that is equal to 2. So this is Sp. Okay, very simple tricks. Okay. Next, so Sp means linear, bond angle 180 degree. Next, NO3 minus, nitrate ion, nitrogen group 15, 15 means 5 valence electron, no monovalent atom attached, so 5 plus 0 plus 1, because this is negative charge, divided by 2, that is equal to 3. 3 means Sp2. Sp2 means trigonal planar molecule. Trigonal planar molecule. Clear? Okay. So in this way we can calculate or find the hybridization of any molecule by applying the simple tricks. Okay. So today I'll discuss total concept of hybridization, and this concept is very much essential to solve the problems of hybridization related problems which may be asked in different examination like NEET, WBJEE or Advance. Basic concept is very important. Okay, so go through the concept and think about it, and practice, more practice give you perfection. Okay.